Hello, in this video we're going to talk about rate laws as part of chemical kinetics. And so I'm going to do my best Jeff Probst impersonation and say previously on Survivor, Chemistry Island. We were talking about reaction rates and how they relate to the chemical equation. And so the reaction rate is the change in concentration over time. Remember, the square bracket is change in concentration. And alright, so for some really infinitely small delta t, you have the instantaneous rate. And, all right, that's instantaneous rate at one point. Now, how does that instantaneous rate vary over the course of a reaction at different points in the reaction? So that's one thing. Then the next is, how can we calculate this rate if we're given where you are in the reaction? Because the rate changes as you go through the reaction. And so that you need rate laws for. Okay. So again, here's an illustration, this is kind of covered in the last video too, that the rate of a reaction varies with time. And so you have time on the x-axis, your concentration of a reactant on the y-axis, and then the rate, the slope at one given point in time, changes as you go through the reaction. Okay, but this rate of reaction, turns out it's directly proportional to concentration. In this table, we have concentrations and time plotted out, and rate also. So at some time, here's your concentration of bromine, and here's the rate of the reaction. So if you take the rate divided by the concentration of bromine, you get a constant, and that's shown in this column. These numbers are pretty much all the same. Now, in this example, we're doing something called a pseudo first order reaction, which assumes that you have a much higher concentration of formic acid than bromine, and so changes in bromine really matter, but changes in the formic acid concentration don't matter because you have a little bit of change compared to a giant concentration of it. So it's kind of a trick to enable us to study reactions that might be more complicated than we want and treat them as a simple reaction where we can only look at the bromine concentration. So now we can plot bromine concentration on the x-axis and instantaneous rate on the y-axis. And okay, as the bromine concentration changes, so does the rate. But this relationship between the bromine concentration and the rate is proportional. So we can write it this way, saying that the rate is proportional to the concentration of bromine. Another way to write the same thing is to say that the rate is proportional to the concentration of bromine. And so this K here is your proportionality constant. And that's what we do. Right, so this K is the rate divided by the concentration of bromine, and so we call this the rate constant of this reaction. And we use this a lot in kinetics. And so here's the example from the table before, that the rate constant's around 3.5 times 10 to the negative 3 inverse seconds. So remember, the job of the rate constant is to make the units work out. So the concentration's in molarity, the rate needs to be in terms of molarity per second, and so your rate constant needs to be inverse seconds in order to make this work. So it is. Now, how does this relate to what we talked about at the top of the video? So the rate is the rate constant times the concentration of bromine. That's this. Now, this is the same thing as saying the instantaneous rate. So we're talking about rate at one point in time, infinitely small delta t, and that's equal to the change in concentration in bromine. So this delta here is important, right? The change in the concentration of bromine over some time frame. And so this idea of change in concentration of bromine over time is like the definition of a rate. But what we're doing with the rate law is we're then using some information that's maybe more easily to obtain to calculate the rate, right? So definition over here, useful thing over here on the left. And remember, this negative sign is here because the change in bromine is negative on its own, so we have to have the negative sign to make the rate stay positive. All right, so some more things about these rate constants. Rate constant is a lowercase k. Keep it lowercase, that's important. Later in this course, we talk a lot about equilibrium constants, which are capital K. And so by keeping them separate, that's helpful, right? You can relate equilibrium constant to rates, but generally we treat them separately. And so it's nice to have some differentiation there. So this rate constant gives you the speed of your reaction. If you have a large K, it goes really fast. If you have a small K, it goes really slowly. This makes sense because, well, here's your concentration, here's K. If K is big, you get a big rate. If K is small, you get a small rate. All right, so this K depends on temperature, right? Higher temperature, a higher K. And K does not depend on concentration because the rate divided by the concentration is K. So K isn't going to thus depend on concentration. All right, so then we take this and expand it a little bit, make it more general. We call it the rate law, or specifically the differential rate law. And this expresses the rate of the reaction in terms of this rate constant and the concentrations of the reactions, not change in concentration, just overall concentration. So if we have our reaction here, A plus B goes to C plus D, and the lowercase letters are the stoichiometric coefficients, the rate law takes this form, where the rate is equal to the rate constant times one component times the other component, and each one of these is raised to these powers. And so we tend to just put variables in for these powers, x and y. And the thing about x and y is that they're not equal to a and b, right? These x and y, these exponents up here are not equal to the stoichiometric coefficients. You have to determine them experimentally. Okay, but these x and y, they do give the relationship between the concentrations and reaction rate. And so we call them the reaction order. So if x is 0, we say this is 0 order, and the rate does not depend on the concentration of A. And so what we mean by that is rate equals concentration of A to the 0. Well, anything to the 0 is equal to 1. So you're saying the rate is unchanging. Okay. Now, if x equals 1, then the rate equals this constant, of course, times A to the 1, so really just times A. So if you double this number on the right, you're going to double this number on the left. So if you double the concentration, you double the rate. All right. And then lastly, if x equals 2, then doubling A quadruples the rate. Because if you double this number and then you square it, that means you're going to quadruple this number over here, right? Now, if we add together x and y, that's our overall reaction order, we call it. So we can say the reaction may be first order in A, second order in B, and then overall third order, right? So when I was drawing on here a minute ago, I was looking at just A, but in reality, you have both A and B and however many reactants you have in this rate law. So I should talk about that if you only have one reactant, your rate equals K times that one reactant to its exponent. Now, if you have 3 reactants, well, then your rate equals the constant times 1, 2, 3 of these, and you go x, y, z. If you have 4 of them, you go x, y, z, and then you have to make up some other letter, right? But so you can expand this to however many reactants you have. And now down on the bottom here, this reaction order is always defined in terms of the reactant concentrations. So when we use the rate law, we're always using reactants only. And that way, we can kind of keep it consistent. And also, it makes sense to use reactants because those are the things you're starting with. You know the concentrations of those typically, and so it's an easier way to go. So how do we determine this rate law? We need to determine both K and the exponents x and y. And so a couple ways to do this. One way to do it is to plot all the concentration versus time data and then analyze that. How does this look? And you can plot it in a couple different ways to tell you whether it's first order or second order. Okay, that's one way to do it. Another way to do it is you look at the initial rate of the reaction because it's easiest to measure that. Dump your stuff together quick, what's the reaction rate? And you can look at that and see how that changes when you do this doubling, right? We said double the concentration of A, double the rate. Well, experimentally, double the concentration of A and see what happens. And so we'll talk about that latter one here in this video. So this is the method of initial rates, it's called, because you're looking at initial rates to figure out kinetics. And so here's an example, right? We've got nitric oxide, NO, it reacts with hydrogen gas to make nitrogen and water. All right, so let's figure out the rate law constant and then the exponents, x and y. So here's the data. Somebody did this experiment, changing the concentrations in a controlled pattern, which we'll look at in a minute, and then measured the initial rate in molar per second. All right, so let me scoot this up. And we're trying to solve for this, right? K, x, and y. So first we can look at, let's look at x. So in experiments 1 to 2, if you look at it, we doubled the concentration of nitric oxide, but left the concentration of hydrogen the same. And that was done intentionally. And so then you can look at the rate. Say, okay, I doubled the nitric oxide concentration. So now the rate pretty much quadruples. It's never going to be perfect because it's experimental data, but you only have doubling or quadrupling, right? So you can round. So all right, double the concentration, quadruple the rate. That means that the X, the reaction order for nitric oxide, is 2. All right, now you can do the same thing looking at the hydrogen. If you compare trials 2 and 3, well, very intentionally, we left the concentration of nitric oxide the same and changed the concentration of hydrogen. And, well, our initial rate this time just doubled. So you double the concentration, double the rate, that's first order. All right, so now we're getting somewhere, right? So we have this. The rate is equal to K, the concentration of nitric oxide squared, and the concentration of hydrogen. And so if anyone asks you for the rate law expression for a certain reaction, it's this thing here. So now we can figure out what the K is, now that we know this information. We're second order in nitric oxide, first order in hydrogen, and third order overall. So you can solve for K, you just take the rate law, solve it for K, and plug numbers in. And you can do this with any of these 3 experiments. It doesn't matter which one. Here they chose experiment 1 to plug the numbers in. Fine. In theory, if you plug the numbers in for experiment 2 or experiment 3, you should get the same K within some experimental variation. All right, put this together and you get K. Now, another funky thing about rate law constants, K, is that the units depend on the overall reaction order. So when you're looking at K, well, remember, a constant's job is to make the units work. So on this side, effectively you have molar cubed, because there's molarity squared times molarity. And on this side, the rate needs to be molar per second. Sorry, let me make that look better. Molar per second. So what happens in the middle here with this constant is we need to have the seconds down on the bottom, and we also need to have molarity squared. So the units on this rate law constant are 1 over molarity squared seconds. That's kind of weird, right? But again, the function of these proportionality constants is also to make the units work out. Now there's another way to do this, and I don't personally like this second way because I think it's too formulaic, it takes too long, and it misses the point. But a lot of students like it because they love blindly plugging numbers together, so sure, here's the number plugging way to do it. So say let's look at experiments 1 and 2, and we can make some ratios here. Just like in math, when you can divide one reaction or one equation by another, here we're doing the same thing. So we're taking rate equals K times concentration of something to the X, concentration of something to the Y, right? And we do that for both trials 1 and 2. Now, all right, we can cancel out the K, because it's on the top and bottom of the reaction. We can cancel out the whole last bit here, which is the concentration of hydrogen gas to the Y, because that's unchanging. So now we have this equation. We have concentration of 1 to the X, and now if you look at this, 10 divided by 5 is 2, and mathematic rules say you can just reduce this to just 2 to the X. Well, 2 to the X equals 4, solve for X. Turns out X is going to be 2. And this is second order nitric oxide. Right? And then from there, you can use experiments 2 and 3 and do the same process again to find the order of hydrogen gas. So you can do this as well, perfectly fine if you do this on a test to have no problem. It's just a lot longer of math and writing as opposed to just looking at this and saying, huh, if I double the nitric oxide concentration, I quadruple the rate. Check that out. Okay, so let's summarize. So if you're zero order in a reactant, it means that as you change the concentration of the reactant, that you don't change the rate. Now, first order in reactant means as you change the concentration of reactant, you change the rate by the same amount. Second order in reactant, change the reactant concentration, you change the rate by the square of the concentration change, i.e. if you double it, you quadruple. If you triple it, you multiply your rate by 9, things like that. So that's the method of initial rates. So now all I have in the rest of this video is another example, so if you're totally good on this, feel free to check out. But here's yet another example of how to use the method of initial rates. So we're going to try to find the rate law and rate constant of this reaction. Fluorine gas and chlorine dioxide makes FClO2, fluorine, chlorine, oxygen 2. There's not really a name for that. So here's the reaction data. And we're trying to find the K, the X, and the Y in our rate law expression here. And so, well, if we look at experiments 1 and 3, you double the fluorine concentration, and the ClO2 concentration is constant. Okay, so we doubled the fluorine. What happens to our rate? 12 to 24. We doubled our rate. So that means we are first order in fluorine, and x is equal to 1. Great. Now, if we look at trials 1 and 2, the fluorine concentration is constant. The ClO2 concentration, we quadruple that. What happens to the rate? 12 times 4 makes 48. Hey, we also quadruple the rate, and this is y is equal to 1. So this reaction is first order in fluorine, first order in chlorine dioxide, and you can say the rate law expression is like this. Now we want to find the constant, and so here's the expression again. Let's solve it for the constant and plug numbers in. Again, you can pick whichever trial you want. I picked the first trial, so here we go. We plug the numbers in, and then out of it we get the K. Now, since this is an overall second order reaction, our rate law constant needs to have units of 1 over molarity times seconds, because we have two concentrations multiplied by each other, and we need to get rid of one of them with this constant. All right, so that's what I have for this video. Thank you very much for hanging in there, and I'll see you later.